Next, we're going to look at the equation of continuity. This is where we transition to considering fluids that are at rest to fluids that are moving. And moving fluids, we often would think of fluids flowing through a pipe or maybe through a river. Typically, we think about liquids here, but really the principles that we're talking about apply to liquids or to gases. It's still generalized to fluids. We just have more experience with liquids moving, and they're easier to see. It's tough to understand when a gas might change speeds or change directions or anything like that as it's moving, because we generally can't see the gases. So let's consider the problem where we have some pipe here, and this pipe has, say, water coming in, but any fluid would work. Water coming in on the left side here where the pipe is wider. And then as it moves, that pipe gets narrower, and so we have water coming out on this end. And we want to know, what can we learn from this change? What is going to be affected with the flow of that water there? So we're going to make a couple assumptions in this case to simplify our problem, and typically these are going to be good assumptions to make. If we're talking about something like water, then this is a very good set of assumptions generally. So first off, we have to have an incompressible fluid. Now, liquids are incompressible, or at least very close to incompressible. That means if you apply a whole bunch of pressure to the liquid, it's not going to change volume, at least by very much. Okay, so water, incompressible fluid, great. Constant flow rate. So that means that however much water we're pumping in on the left side here, we just continue to pump that same amount. So we don't change and start pumping a little more or a little bit less halfway through our problem. So if we do that, then that's going to affect the rest of this. Good. Consistent flow rate. So that also means that at any other point along this pipe, that the flow rate is going to be consistent as well. So the amount of water going past this point stays the same the whole time. The amount of water going past this point stays the same the whole time. Everywhere in the pipe has a consistent flow rate. And then the last one is that we're dealing with a non-viscous fluid. Viscous fluids are ones that we think of as thick, like molasses or honey. Non-viscous fluids, those are the runny fluids. So water is a non-viscous fluid. So we need to make those three assumptions in order for this to work. So next up, let's redraw this with a few modifications. So we got our pipe, and it's going to get thinner. Our pipe, it gets thinner. Go. And then let's look at two different sections of water moving through this pipe. So let's look at just a cylinder that's here in this thick section, like that, and then a cylinder that's here in this thin section. Okay. And then we'll just keep things general here, so let's just name some of these different properties. We'll say that the area for this section, we'll just call that A1, and that the distance that this section, this plane of water, or this little circle of water travels in some amount of time, we'll call that just delta x1, the change in position. And then over here we'll have A2, and then this is going to be delta x2. The amount of time that passes from A1 to A2, we'll make that, from this part of A1 to the next part of A1. So when this circle moves from here to here, or this circle moves from here to here, we'll just make that consistent. So we'll have some time involved, delta t, that will be the same for each of those. And then we're going to be assuming that this section is moving at some speed this way. We'll call that V1, and this one's moving at some speed this way, V2. Now, we can make some qualitative predictions about this before we do any calculations or derivations using equations. If we have this big, thick pipe here at this section, and we have a whole bunch of water there, a lot can fit into that big, thick pipe, and it's moving at some speed, and then suddenly it starts to get compressed here. It's still moving over to the right, but it doesn't have as much space to occupy. Well, it can't be compressed. It can't be squeezed into a smaller area. So it still has to take up the same amount of space, still has to have the same volume, and behind that area, that's taken up with water that's coming from the inlet of this pipe. So the only way that we can make this work is if this little circle, or this little cylinder of water, if that expands forward. So in order to do that, it's not only going to have to be thicker over here, and I should draw it that way, not only going to have to be thicker, it's going to have to move faster. It needs to get out of the way of the water that's behind it. And so we can qualitatively understand that the water is going to move faster over at this end than it does at this end. Now, you have a working knowledge of this already because you've used a hose before at some point, I assume, and when you want to make that hose spray farther, what do? Well, you put your thumb over part of the opening of the hose. You close off some of that area for that water to move through, and that water sprays out farther and it sprays out faster. So this is an idea that we already know. We're just looking for a mathematical relationship to describe this and that we can work some calculations with in the future. So let's say that this whole section has a volume, and we'll call that delta V1. And this one has a volume delta V2. I've got the V for speed and the V for volume, but I'll use a delta with the volume. So how much volume has passed through this area, we can think of that, how much volume has changed from one location to another. And so we'll always use the delta for volume, we'll just use the V for speed. So we should be able to keep those straight. Okay, so if we look at our diagram, the volume for these cylinders is equal to the base of the cylinder times the height of the cylinder. These are given to us. The area of the base is a known value, or we've got a variable for it, and the height, or the depth of that cylinder, is expressed as well. So delta V1 is equal to A1 times delta X1. And delta V2 is equal to A2 times delta X2. Okay, so I'm just using the measurements. This needs to be extended now. There we go. Just using the measurements that I labeled earlier on here. Okay. Now, A1 delta X1. If we wanted to know how far that little section of water had traveled in a certain amount of time, we could calculate that if we knew the velocity for this, and that's a variable that we have set up as well. So let's change this. Delta V1 now is going to be equal to A1 still, but instead of delta X, I'm going to write this as speed times time. So this is V1 times delta T. Now this is nice because I'm starting to work with a common variable, this delta T, for each one of these two equations. So that might be a point where I can combine these two equations. And then for delta V2, we'll have A2, and then instead of delta X2, we'll have the speed times the time. 2 times the time. Okay. So at this point, we've got expressions for the volume that has to pass through each one of these sections, and we know that since we're using the same time for each side, we must have the same volume here in section 1 as we do in section 2. If we didn't have the same volume going into this compressed area, or this smaller diameter area as we did coming out, then either water would have to be disappearing, we'd spring a leak in the side of the pipe, something like that, or we'd have to be inventing water. We'd have to have brand new water. So delta V1 has to equal delta V2. We have the same volume going in as we do coming out. And then we have expressions for these. We've got A1 times V1 times delta T is equal to A2 times V2 times delta T. And we can see that our time appears on both sides of the equation. So since we know that the change in time is never going to be 0 here for any problem we would want to do, we can go ahead and divide both sides by delta T. And we get A1 V1 is equal to A2 V2. And this is what's known as the continuity equation. And it's this equation that was our end goal, to express how the movement, how the velocity, in this case, changes in a pipe where the diameter changes, or where the area that the water can occupy changes. So we find that the area times the velocity is going to be a constant value for all of these different points in a pipe. And that's another way that you see this written sometimes, is K is equal to AV. So the area, the cross-sectional area times the speed is equal to some constant K. Typically we'll work with this first version of the equation though. So if I went from an area that was large and a speed of V1, and then I ended up at an area that was smaller, since area has gotten smaller, velocity has to get larger to compensate for that. So when we go from the large area to the small area, this section must be getting faster, which is what we expressed earlier qualitatively. Now we have an equation that expresses the same idea.